All right, everybody, welcome to another CyberSec Tuesday. Tonight we have a special guest. We have Glitchbunk coming on doing a talk about Windows file systems, specifically around NTFS, master file tables, and the whole entire boot process. So stay tuned for that. I just want to give a quick shout out to our wonderful sponsor, ArcLight 6. They've been sponsoring us now for a few months, and they're helping us promote No 404 and bring out promoting our upcoming DEF CON celebration party that's going to be going on. So if you're interested, ArcLight 6 is a consulting company. They focus on cybersecurity engineering and networking and software engineering. So check them out over at arclight6.com. But feel free to take it away.
Thanks so much. Hello, everyone. I'm Glitchmonk, and I'm super excited to talk about NTFS. A little background, especially as to why I'm doing it on this. I mostly work in interdisciplinary cybersecurity, so any place where cybersecurity meets something else, where software meets hardware, where the screen meets a person, anything like that's super interesting to me. And especially here, it's so easy to go down a rabbit hole and learn so much about things that could actually affect you when you're trying to understand how things work or trying to try to break things. So with NTFS and file systems, we are first going to get into what a file system is. So we start with in general, when you have a memory hard disk and you have a bunch of zeros and ones on it, your computer has to figure out how to convert all of that into your actual files, your videos, and actual software. How it does that is generally through a system, a pre-designed system that's supposed to work with your hardware capabilities, supposed to work with your software, and in the end, it's supposed to have the most optimal organization. So you can store your files, you can retrieve them, and hopefully there is some security to it, which means not only that it protects you from attacks, but also some amount of redundancy so you don't accidentally lose your data. I like to think about this as how you would stack a bookshelf, especially how you would stack it if you were in a library. You want to be able to find the book that you want, but there is no way to easily do that unless you have an organized process. Specifically, if you wanted to point somebody else to a specific book, you would start with which section it's in, which bookshelf it's on, which row it's on, where a certain author begins or where the title names begin. And there are different ways of doing this. I know some people like to sort books by height, which is strange, or color, which is worse. But somehow you're supposed to know how this is being done, and the OS is the one trying to understand exactly this process. So you have a bunch of different OSs and a bunch of different file systems. They all do these things in a different way. There are many reasons as to why there are so many file systems. This is not at all an exhaustive list. There are so many of them. The reasons are one that it mostly started as proprietary file systems. In fact, a lot of them were closed off, could only be used by, say, Windows, things like that. But then behind the proprietary nature of it, there's also the fact that you're probably working with a specific hardware, specific software, and you want those two things to mesh together really well. And if you standardize that, you would have to give up a lot of other proprietary things, like how your kernel works, how the hardware that you're currently using works, etc. When it all started out, we only had FAT, so that's file allocation table. This is how floppy disks store data, and that was pretty basic, pretty easy, just straightforward. This is where the data is. This is how far you have to read and then stop. After a while, we had exFAT. The first reason why exFAT started out was because you wanted larger memory sizes. With FAT, you only had about 4 GBs worth. With exFAT, you have this extra feature that it is compatible with almost every OS, or most OSs. I would say that it's not the best one for a particular OS, but if you wanted that sort of cross OS usability, this would be the best. APFS is Apple's file system, so that's what Mac OS uses, that's what iOS uses. You have a whole bunch of them for Linux. Obviously, you have ext4, which is more common, I suppose. And finally, you have NTFS, which is what we're talking about today, which is Windows. This was developed by Windows. Before this, they used only FAT, and after a while, it just didn't work out. They wanted a whole bunch of new features. And NTFS specifically now is what Windows uses all the time, but it's not exclusive to Windows, so you could use it on something else. You also could get very few, I guess, custom file systems for your specific reason. And again, this comes down to whether you want a super optimal way of organizing your bookshelf for your specific needs. You have one shelf that says the books I read on Wednesdays and Thursdays, things like that. I think a good example is DeepSeek AI has its own file system, completely its own, and it's because there's just so much data and it needs to access it in a particular way. Oh, and of course, if you use the wrong one, it's not gonna work, like the little um, error that you see there. But specifically for NTFS, this is one of the most popular, maybe the most widely used, probably because there just is a lot of Windows out there. It's considered to be much more superior to FAT in a lot of different ways, and this was by intention. It's supposed to fix a lot of flaws, but also add a lot of new features. One of the most important feature is metadata. So you have a small section that's reserved just to hold a metadata of different types. The most important is probably the MFT, or the master file table, but you also have other ones below. You have a few more that I haven't included here, but they're honestly not immediately relevant. The most important ones are boot, MFT, bitmap, log file. So you start off with your boot sector with, like in the image, you can see how that's the first thing that you see. After that, you have some of the other metadata files. This includes the bitmap, log file, things like that. Then the MFT, and then finally your actual data. So those are your files and things. You also have a lot of redundancy, and we'll get to some of the more interesting features that NTFS offers. So you have backups of the same thing in case one gets corrupted. You can always go to the other and reference that instead. Your boot is where you start. Your MFT is where you get extra information about your files and your records. Your bitmap shows you what clusters are being used. So most memory, I guess, partitioning uses clusters and sectors. So that's just how you break up a huge chunk of information into smaller ones. Your log file has a bunch of transactions, which is how your files have been accessed, where they've been copied, things like that. Definitely used a lot when something crashes and you need to recover. So recovery is also pretty important step. You can't always prevent the disaster, so you either have a backup or you recover it somehow. For Windows specifically, NTFS has been really great for many reasons. There are a few reasons that where it's just working, no one wants to fix something that's not broken. But if we are going to go into something that's different from NTFS, it's probably going to come from Windows itself. It would be quite hard to build something outside of Windows for something like this, even though a lot of such options do exist for other use cases. For NTFS, it actually started on an operating system called Windows NT. It's really old. It's even before XP, and I guess XP is considered old also now. So you had, that's where the name comes from, NT. So you had the breaking point where people did no longer could just use 4 GB fat file systems, so they had a new one come up. The most important feature here was access control. So you had permissions for users and groups, similar to how you would very easily do it in Linux. You still don't need to do that in Windows, but you have the option to. You also have recovery, so if something goes wrong, this is especially true when, say, you have a USB or copying something and then the USB just falls out. If you are on a FAT file system, it's more likely that either you lose your data or it gets corrupted, something like that. With NTFS, you have a much higher chance that things will be preserved as much as possible. This also prioritizes extremely all the space on the volume. Instead of just assigning a bunch of space for to be used in the future, it usually figures out places where you could add in more data by looking at how many zeros are out in the file system, in the partition. And on top of that, this um, is included for things like compression. So you could compress your files and then you can still use it without having to manually decompress it. Unfortunately, it does still compress and um, decompress behind the scenes. So there is a performance overhead for this, but at least you are trying to use all the memory available to you. And there's no really, I guess, things that are closed off unless it's reserved for its actual OS use. You also have faster speeds, fewer bottlenecks, and a custom integration with the kernel. This is why it's very difficult for you to sort of make another file system that could be better for Windows. Some of the optimizations that they have doesn't actually work for Windows specifically, even if in theory it's supposed to work better than NTFS. When you use the same thing with Windows, it doesn't work so well. So there are better features out there. There are probably better things you could do if you aren't using Windows, but it just does not fit for this use case. We're going to start with boot. Boot is the first thing that you see, absolutely the first thing. I would, I guess, relate this to, say, you are looking for a book in a library, you just walk into the library and it just overwhelms you with all the books all around you. But then you see a little sign that says, I don't know, romance novels, arrow pointing this way, and you kind of know where to go from there. So the first thing that you see would probably be a bootstrap code. This is generally how things just boot up in most OSs. But in this one specifically, you have something called an initial program loader. So what does this do? Apart from the basic init programs, making sure everything's in order, it tells you where your partitions are located. You want to never be in a memory location where you're not supposed to be, or where there is nothing, or where you can't get out of it into something else. You also want to know where exactly you want to go once whatever you're reading has ended. So it's important for you to know where actual data is stored and where everything else is just garbage or it's empty. How this is done is to immediately find the MFT. So you have a location in the boot that tells you where the MFT is. And this is usually how low-level programs run. You always have some location that tells you where to go next. So the absolute first byte that you see has to be boot, because you don't know where to go when you're starting out. And then finally, it has to be the MFT. There is, of course, redundancy here as well. You have the other MFT, the backup MFT as well. Make sure that even if something's not so, if there's some parts of the boot that's corrupted, you still can recover it. And that's a huge part of NTFS as well. Really tries to recover certain parts of code that is corrupted, not just by bypassing them, but also trying to fix them. Your MFT, which is where you head up next, has a file, has something called a record for every file on your drive. Your record usually has a sector dedicated to it. Sometimes that doesn't happen, usually. And it has all the metadata that you need. We have a full breakdown about this a bit later. But the metadata, of course, has stuff like when was this file created, how big is it, how, like, where is it stored, things like that. But also sometimes you have resident files. What those are files where the entire data is completely stored in the metadata. And what this does is it makes things go faster, because you don't just read the metadata all at once and then go looking for the files elsewhere. You just have one little box that says, this box only has the Harry Potter books. It's only Harry Potter in there. You don't have to go searching elsewhere. In something like FAT, you would probably need to first find the location of a table. In that table, it will tell you whether your file exists. And then you have to go to another table that'll tell you where the location is. And then you have to go to that location and then you see the file. So that's much, much slower. Some configuration tips when you are, I guess, starting out formatting for Windows or for NTFS is always do it for Windows. Do not try something else. You also have a thing called journaling, which you can access and you can look at, try to do something about when there are crashes and also when there are changes. So a lot of antivirus programs, they really benefit from this because instead of always scanning your entire device, they kind of look at this journal and figure out what's been changed, and only that gets scanned. This is also great for other things like data recovery, for crashes. It's also important for forensics, where you want to see what happened and when it happened. Um, in general, journals are something that you have access to. You could go look at it, and there's a whole bunch of links I've added at the end as well, which talk about journaling, talk about access control. Access control is a fairly more of a familiar process. You just add permissions to each file, each folder, things like that. You also have something called quotas, I think, where you can make sure that a user only uses a certain amount of a drive. So say I have a C drive that's 80 gigs. I can have a quota for this one user who likes to, I don't know, save all of his Twitch streams, and say, no, you can only use maybe like 10 GB. You can also encrypt your files. So BitLocker, things like that, it's very much based on NTFS, very close to that. You could also compress your files, and while compression does work, I don't think it's very intense, and it also does add that performance overhead. I don't think we care too much about that overhead now. Maybe it used to be a much bigger thing before. You have a very special thing called a mount point folder path, which is where you can use your drives like a folder. And this helps when you're trying to do some things on the terminal. It's a bit of a, I guess, power user tip. I've heard somewhere that you could have a drive inside a drive. I have not tried this. I might be spreading misinformation here, but that would be pretty cool as well. Finally, you have, so again, the whole reason that works where you have a drive and then a folder is because file systems are generally structured similar to your trees, your file system trees, like how you see on your Explorer, your file explorer, or on Linux. So essentially, even though we call it a drive, we call it a partition, you still are in some sense using a folder. Finally, the best part for using Windows and NTFS for larger structures is where you have something called soft links or symlinks. This is a feature of NTFS as well, where when you're copying something, you don't need to copy the entire actual data. You just make a link to it. This is a fairly common thing that we do, but it did take some amount of effort to get that going. The reason is that usually you don't have something that can point to a different area in a different sector directly, or a different drive entirely. But soft links do make that happen. So you could have one huge file and then several people having their own versions of that just through the link. Some of the common things that I've seen when people are starting their home labs, and I guess they're just messing around, trying to try something new. These are very small pains, things that you will probably get through by reading maybe 20 links on Google. But the reason why these things happen, which is quite interesting to me, is somewhere in the file system, something's going wrong. One part of that is when you have these tinier devices, like you have a USB that you want to use between platforms and you don't know why it keeps telling you to format it every single time. Definitely have seen many of those little pen drives that sadly keep losing their data and have to get rewritten every time, please use exFAT instead. Apart from that, external drives for weird hardware. So this is with smaller chips. Your Raspberry Pi can probably support NTFS, but with a lot of pain. So instead, use something else. You have the same with, I think, security cameras I've actually seen have their own file systems usually. And that makes sense because of the amount of the volume of information you want to write when you're having a stream like that. And you probably have the SD card or whatever formatted by the device itself, things like that. So that's great too. So the next thing is something called alternate data streams. This is a really interesting thing that probably needs a very long time to explain properly, but what you can do is make it so the file system is accessing multiple things at the same time, but it is to functionally serve one purpose. But by doing that, you could open yourself up to a lot of vulnerabilities. And making those vulnerabilities happen is actually a pretty interesting side project, or I guess a little challenge that you can give yourself. There are links to this as well at the end. Finally, you have BitLocker and Dual Boot, not specifically related to NTFS, but definitely because of the new restrictions on encryption and that going back to the file system. You probably need to go in and do a lot of settings changes when you want to do your dual boots. Probably a good idea to prepare before doing this, because the risk is losing all of your information. Adding more memory to an existing VM is something that I have spent way too much time on, not just for me, but for other people as well. This is one of those things that just seems to be a pain, and every single time you waste so much time on it. And so I just have up the easiest way of getting it done, especially for Windows, is you open up your VM, you have your VM that's already set to say 2 GB, not good enough, and you want 30 GB more. You add the 30 GB when the VM's powered down on your VM software, but then it still does not get added to the computer. And a lot of people, especially if you're using headless, um, don't really even see that they're still at the same memory point, and now you are struggling to do the thing that you were trying to do. Instead, remember this picture that shows how it is unallocated. So that means that when you added extra memory to your VM that already was created, the VM was created with that C drive that shows like about 50 GB, and that has NTFS, but the rest 30 is not allocated. What you want to do is to, if anyone's used disk management before, this is pretty easy. You just try to resize that partition so it takes up all of that space. But sometimes it's not easy to do. Some of them don't like being moved around like that. And since you are currently using the C drive, it's very difficult for you to rewrite those parts of the file system that you are currently using to also get the unallocated part. So you can reshape the thing while you're using it, but you can't reshape it when it's off either. So what do? You use a tool called gparted. So gparted is basically for GNOME, but here what it does is it boots up as an ISO separately. And once it's done that, it'll show you what you could do with all the unallocated space that's available on your system. This is not the same system as the other picture, but as you can see, you have all the functions necessary to resize something, to delete something, and once it's saved and you restart, removing the ISO, you now have a bigger VM. I have definitely seen a lot of tears over this, and I'm sure after a certain point you know exactly what to do, but it still feels like a bit of a pain. And once you understand how NTFS works, because you have that organized way of doing things, it's like someone else just came in with their bookshelf that they've arranged in their different way and want to join it to yours, but you're like, it just can't, you can't just drop it right next to it. This is also true when you're formatting your USB. This one's pretty easy. All you do is press a button, you just say NTFS. But how specifically softwares like Rufus, where it creates that bootable USB, um, it's pretty interesting. I just linked this here because it's a very long explanation, but I really like learning about these things, even though I specifically don't code that kind of software. I just use Rufus. It's interesting how you can't just copy paste every byte over from the ISO for it to be a bootable USB. There's actually a lot of things happening in the background for each one of these file systems to make sure that the file system understands the order in which this ISO is working, and then you can actually boot it up. And the fact that it can do it for so many different file systems is pretty great. I do think um, the developer also is very good at explaining how they work. So why is all this important so far? Sometimes diving deep is good. I know that the NTFS itself probably is not the focus for many people in cybersecurity, but sometimes when you go that deep down, you see exactly why things that are slightly irritating you when you're trying to do something actually mean a lot to maybe the computer or the process that you're running. There's always some reason why the bug exists, even if that reason is not very easy to see. But sometimes it's also good just to get it working. You can sit and read about how every byte is stored on the file system and then never do anything with that information. But it's kind of nice when you can play around with these file systems yourself and figure out um, how a computer even runs. The next thing is that foundations really do help. I felt like I was picking up a lot of tips about the foundations and it didn't seem helpful, but then I definitely noticed a speed when I was actually doing, say, a CTF, a problem that I've never seen before, or something, even if it did not um, resonate with the things that I already saw, it sort of followed the same architecture underneath, and so I could get my bearings. So these things really help in speeding you up in ways that you wouldn't notice directly. Finally, you have VMs and USBs, which are something you will be working with a lot. It's it's really good for you if you can understand exactly why these things are giving you a heartache. Same with BIOS settings, things like that, UFI. But then again, you have these patterns that occur over and over again. So once you understand exactly how the organization of this bookshelf works, you'll see the same pattern in a lot of other memory management. You'll see that in a lot of, I guess, code where you want to look at the byte level structures. And in the end, it really is about how these standards are made and maintained. Right now, we definitely will be using NTFS for a very long time, and it's because you have so much relying on it that a new standard has to be either a much more efficient, be much more secure, and C, it has to be something that can be shifted to pretty easily without losing a lot of backwards compatibility or things that are already here, right? It's much easier to have a box of packed books and then give a brand new way of stacking them on a shelf than it is to pull down all the books already stacked quite neatly and then put them back in a new order. The next thing, yeah, this is probably just links that would help you to go a bit deeper on each of the things that we talked about today. Especially, I would recommend going through the Digital Investigator blogspot link, which would probably show you how a forensic evaluation of NTFS would work to a small example about this too. The other thing is Gparted, the tool that we talked about, has so much interesting documentation. So that little picture that you see there with the list of blue links, that is all from Gparted, and they're so long and honestly quite interesting. So you have everything about exactly the way why things work the way they do. Back to the old days where You have to read the documentation. Maybe your AI can summarize it. But I had a great day actually looking through one of these. I think the one that says UID partition. That was pretty good. Finally, for anyone starting out just now, this is something I promote every time I'm speaking. It is called the skill tree. There's a whole bunch of these at the link down there on GitHub, and there's a whole bunch of different ones as well. I think there's one for baking. It starts out really easy, where you can pick your task for the day and then color it in once you're done. And it gets pretty hard up at the end. It definitely helps you see your progress as well as figure out where to go next. Sometimes the next project that you see might seem too easy or too hard for you. I thought that this skill tree is a great way to keep going. So do you want to go deeper into NTFS, really look at every single thing it's got? Do you want to go into sort of what did we build off of this and get a broader understanding there? This final part is a much deeper insight into exactly what looking at NTFS looks like. This is the MFT table, and I have stared at this way too long. This is a program called WinHex. It is free, and I would suggest you could just download it. You could use it on your computer. There's really no, I guess, downside. Great way to understand exactly what's happening on your computer. We will go through this. I hope you can see my mouse, but you see here tools, and it's okay if you zone out at this part. I know it's quite overwhelming. But you see here stuff that you would see on your computer. So here you would see program files, users, things like that. But you also see the metadata files that we were talking about before, like bitmap, boot, the MFT log file. So you have a few more that we didn't talk about as well. And you have all of their metadata as well down here. And this part is exactly how your bytes are actually stored on your drive. So this is what we were talking about when we meant books in a library. It's very hard for you to just figure out exactly what's going on unless you have a system as to how to go about it, right? You have something that converts this to ASCII. So you see here it says NTFS, you know what you're dealing with. But apart from that, what you're going to be relying on is this thing called offset, right? So offset tells you how far you are from the first one. Your offsets and another thing called size, which is how big is the thing that I'm reading. For NTFS, that would be like 4 characters. That should be 4 bytes. But where do I stop, right? I need a place to stop. Either that's by size or that's by a particular code that tells you this is the end, right? Like that signifies stop. The third thing would be certain names. So some specific things are special indicators of either a certain file type, the end of a sector, or something like a specific attribute. So they have specific numbers, like actual numbers. So with these 3 things, you should be able to triangulate exactly where you want to be. Unfortunately, there are offsets to offsets, and that's where things get a little more confusing. Before we go deeper into that, there are 3 things about reading literal bytes that I want to explain for anyone who's unfamiliar with this. One is that how offset works is that it counts each byte. So this would be 1, 2, 3, etc. But it is in hexadecimal. That's why you see 10, 20 here, but there are 16 down here, right? You also have little numbers here. So if I quickly want to know where this 20 is, it's 8 plus 0. So that's 8. So this 0, 0 is at 9 plus 10. So that would be 19 in hexadecimal. The last thing is that this is in little endian, which means that some of these things most probably are read backwards. So if I wanted to read these 4 things are important to me, I actually have to go backwards. It's 0, 0, 2, 0, 2, 0, 2, 0. That's how it works. Um, for this to work, we really need to depend a little bit on the bookshelf analogy, right? If I wanted to find a specific bookshelf, someone tells me it's the third bookshelf down the right, and it's on the second row, and it's the second book down, and it's, I guess, the fifth chapter in that book, right? So you start counting the number of bookshelves, you get to the third one, you start counting the number of rows, so that's like one and then two, and then you start counting number of books, it's one and then two, right? So it works very similar to that. Another way that you could probably think about this is your address. You're trying to like close in lower and lower to where you actually live, from your like city to your I guess your neighborhood, your house, inside your house, which room, like your fridge, the freezer, the ice cream. So you're getting closer and closer to something specific. This is an example of what you would see in an MFT for a text file. Like we said before, MFT happens for a record happens for each file that you have. So this file is a text file. And so usually in CTFs or in, if you're taking, I guess, a forensics class, you would probably be looking at something like this, where you either see the metadata of the file or the file itself. As we talked about previously, the resident files are files where the information is so small, it's completely inside the metadata itself. So if we had to like scroll down here and this was a very small text file, you could probably literally read what was inside the text file right here. The other thing to keep in mind is that you see how this starts with file 0 right next to the line. That's usually how every record starts. It's right next to the line, which is where the new sector starts, and it probably has some indicator as to what kind of file it is. It also has something at the end that tells you that this is the end of this file, right? There is I didn't go too much into detail on exactly how this works, but essentially you have all the metadata up here, a little more data on if it's a very large file where the data is stored somewhere else, you need the location of where that somewhere else is, or that's going to be lost forever. So the metadata has both the amount of information in the metadata about the file and also where the rest of that file is stored. When you are trying to figure out something in MFT, most of the problems that I have seen starts with magic numbers. Magic numbers are signatures for each file. So you have a gigantic dictionary of these numbers. They're usually 4 bytes long. They could be 8, and sometimes they're just 2. But what this does is tell you specifically what file type it is. So the file extension that you see at the end, some of them are shared, like you see here, all 3 of these share, I guess is a bad example, but there are quite a few that are similar, like say Excel files, Word files, even though those are different kinds of files, they kind of share the same signature. So when you see this, you might not be able to read it in ASCII, but you know that these bytes mean it is an RPM package. Similarly, sometimes they are in ASCII. So when you have an SQL like file, it will literally say SQL. So right here, it literally says file 0. Every single text file has that. Similar to PDF files, actually. I think they say literally PDF when they begin. A lot of them don't do that, so that's not something you can rely on, but many of them do. Then you have attribute lists. So you have a list available, right, that tells you which parts of these are important to you. Here, there might be other metadata that is important to the computer, but not so much to you as a person. You want to find attributes which are blocks of metadata that is important. So in this case, this 10 is considered one of these attributes. And this 10 isn't just these 4 bytes, it is this entire section, right? So since it's that entire section, there's very specific information stored continuously through this. It's almost like matching that table to these bytes through the sizes, right? So in the beginning, every single 10 attribute would have these 4 bytes that go 10, 0, 0, 0. you would have the size of the 10 attribute, which in this case is 60 bytes. And 60 bytes, if you think about it, is count this as, I guess, 8 and count this as 10. So you have 10, 20, 30, 40, 50, and then like 60 down here, right? So this entire section is 10. And then you have stuff down here, which is more important. These are important, but stuff down here would be your when was the file created, when was it modified, when was it deleted, things like that. And as you go lower, the other ones have similar things as well. Stuff like where is the file located? Is this a resident file? Things like that. So you just have a bunch of those. I've sort of highlighted this for time because you can also see the time here. If you were to convert this okay, it does take a while to convert this. You have an automatic converter, and you can kind of see that somewhere here. You have something that automatically converts that when you select it. But if you selected this, it should give you one of these times specifically, right? The other thing is this offset here is a really big number. But what that means is where your file is stored from the very start of the drive. So your C drive's very first byte to here is this gigantic number. So in this way, you could probably figure out every single file that's on a system. You could figure out secrets. A lot of flags are stored either in the metadata or in the like file data section. A lot of times they will ask you to do some amount of byte, I guess, conversion. You might have to reverse this. You might have to, I guess, do some operations on it. And then you probably will get a flag. I did see one weird challenge called Master Phantom Tax. And now I've said that in public, which was completely about MFT, very fun. And I would definitely encourage you guys to try it because everything to do it is free. There are write-ups that are out free. And some of them do give you some insight as to how normally your files are being stored. Does give you somewhat of, I guess, sympathy for your computer doing all this hard work. Um, we've gone through all of these, but I'll just go through it really quickly again. You have your magic numbers, which is what kind of file it is. You have your attribute list, which are chunks in your metadata that tell you specific things about a file. Each attribute has its own list of fields, so every attribute always has those fields, so you know exactly where to look for your information. What's important to you is the offset of the file, which is how far is this from the very beginning of this entire drive. You have offset from the signature, which means how far is the data, the metadata that you're looking for from the beginning of the file. Then you have the offset from the attributes. So since you've chunked your metadata into attributes, you also want to know how far your specific field is. Is it the fourth, I guess, row in the table called attribute? So that would be some examples would probably look like this. And then you want to know size, how far before I can stop, right? Especially because we have little endian here and you're going backwards. If I were to use even one extra byte, that would probably mess up a lot of things because this is the most significant value now. So I really need to know exactly where to stop when I'm looking at these bytes. Finally, you have some special things like the signature, like the attribute header, and like the end. And in this case, the end is always F503. So every single file, especially in the MFT table, ends with F503. And that is where I end as well. Thank you so much for listening. Please let me know if you have any questions on anything we've spoken today.
Hey, great talk. That was very in depth, which was awesome.
Thank you.
Yeah, I really liked, and I posted in our meetup text, the security tree where you color in from basic to advanced in IT security. I think it's super cool. Thank you for providing that.
Absolutely.
So, what got you interested in into diving down the kind of like the file system route?
So I think inside me there are two wolves, and one likes to go really deep into a subject, and one likes to go really broad. Definitely interested in interdisciplinary security because of that. And for some strange reason, things like assembly code, how exactly does this thing come to life, right? That always has interested me. There has been this one course, I'm guessing it's on Coursera, but I don't know if it's still up. It's called NAN to Tetris. And it's something that I promote a lot, even though like no relation or anything, where you go from a NAND gate, which is like a logic gate, right? Two zeros make a one, whatever. And then you go all the way to a computer that can play Tetris. So you program the Tetris as well, and it plays Tetris. And those kind of things have always interested me, where not only do I want to learn how I can, I guess, tweak something or how I can stress test something, find a vulnerability, but also exactly how it came to be like to a very deep level. This has trade-offs. You could become one person who's working on one kernel, on one version for one specific thing for your entire career, or you can become a person who, I don't know, uses like, I don't know, a bazillion different tools every single day, and then new tools are still coming out every single day, and still get stuff done. So I really like to try to find the balance between the two.
Cool. Yeah. And do you have any? I know you mentioned. Did you mention Try Hack Me?
I
I think I might
did.
have saw that. Did you say there was
Yeah.
any like hard drive forensics things on there? Have you seen?
I'm not. I definitely have seen stuff related to file systems quite a bit. I don't remember if that was strictly data recovery kind of things, but there are definitely ones related to forensics and ones related to memory specifically.
Got it. Okay. Okay. Cool. Anyone else have any questions for Glitchpunk?
No, that was awesome though. Thanks for the talk.
Thank you so much.
Yeah, really good.
Are you normally working in cybersecurity or more like on like just the technical side?
It is a little transient. I am mostly in security now, but it ranges from like teaching to just as a hobby finding vulnerabilities to um working on like smaller projects and gigs like that. So it is a bit all over the place.
Okay, cool. Yeah, I mean, I feel like that's how most of us are.
It's a fun way to live.
Oh yeah. Oh yeah. Well, cool. Well, feel free, anyone, if they have any questions, feel free to reach out to Glitchmonk. Do you mind sharing your slide deck at all?
Oh yeah, absolutely. I mean, I don't mind. I will.
Cool. Yeah, just drop if you want to put like a PDF or whatever you want in the channel. That'd be appreciated. And then if you have any ways for folks to reach out to you, whether it's just Discord or LinkedIn or whatnot, feel free to add that as well.